Okay, here we are again, another week, another lab. This time it's the Introduction to Acids and Bases. I'll tell you right now, I'm going to cover a lot more material than you need to be able to do this lab. And the reason for that is it should help you in class. It's stuff you should know, but also because it forms the basis of where we're going to go with buffers next week in next week's lab. So you need to know this to be able to really understand buffers. So I want to cover it now since there's not really a lot that for acids and bases, since this is the introduction, there's not a lot to really kind of understand for just pH. But I want to get into weak acids because that's where buffers come. And that way I won't have to spend an hour next week, but we can get it done this week. Okay, so that's why I'm doing what I'm doing. First off, when we deal with acids and bases in chemistry, we're dealing with three different definitions. And the first definition came from Arrhenius. He was studying them a long time ago. He's really the one that came up with a lot of this. And he said that acids produce H plus ions in solution. Well, he was dealing with aqueous solutions. And in aqueous solutions, you're not going to get any H plus ions. You really get H3O plus ions. That is a proton added to a water molecule. H plus would just be a proton. There's no protons in water that are just swimming around. They get attached to a water molecule and form H3O+. The other thing he said was that a base was something that formed hydroxides. His definition is good. We'll use it. You can use it. You can see where it's going to be a good definition for what we're going to do. But it's very specific. It's only for things in water and only for things in water that produce hydroniums and produce hydroxides. So it's a very, very specific definition for acids and bases. Good one, but very specific. The next one that came along was Bronsted-Lowry. Bronsted-Lowry came along and they said, well, we're going to say that an acid is a proton donor. Okay, does that make sense? Well, H3O+, what is that? Well, that's a water molecule that has an extra proton on it, right? In other words, if I take a proton and add it to a lone pair of electrons, that forms a hydrogen bound to that element. Because that's all this is a proton with a pair of electrons. Proton with a pair of electrons. Proton with a pair of electrons. Lone pair of electrons. But it's the same thing. So certainly this meets the Bronsted-Lowry definition, right? Something donated a proton to this, and it formed hydroniums. So that was a proton donor. That was an acid. He said, then Bronsted-Lowry then said that a base is a proton acceptor. Well, hydroxides can certainly accept a proton, right? Because they have three lone pairs of electrons. Has a negative charge. This has a positive. So certainly a proton can be donated to this lone pair of electrons. It will take those lone pair of electrons and it'll turn it into a water molecule. Okay? Because again, this hydrogen bond there, it's the same thing as a proton sharing a pair of electrons. And I have a non-bound pair of electrons there that can be shared. The third definition was Lewis, and Lewis was very, very general. It incorporated both Bronsted-Lowry and Arrhenius. It's not used as much. Bronsted-Lowry is very valuable for some insight you can get from it. Lewis acids and bases are very general. They're a little bit tougher to remember because they deal with electron pairs rather than protons, and they kind of go backwards that way because of to Bronsted-Lowry. That is, the Lewis definition of an acid is an electron pair acceptor. That's an electron pair acceptor, not an electron acceptor. So certainly for this to have gotten that proton put on there, it had something that accepted an electron pair, right? There was an electron pair acceptor. The base is an electron pair donor. Well, certainly a hydroxide has an electron pair to donate. So it works. It works. It's just much more general when you get into that. The easiest one is the Bronsted-Lowry and Arrhenius, and they kind of overlap so much. Bronsted-Lowry and aqueous, so same with Lewis, but Bronsted-Lowry and aqueous is essentially Arrhenius. Bronsted-Lowry has specific cases where it's easier to understand, and Arrhenius is valuable in some cases too, except that you never have H plus inside there, even though you use that shortcut sometimes. So that's the three definitions. Then we got to get into pH. So what is pH? Well, P means, it used to mean potential, now it basically means the negative log base 10 of something. Since that's H, it really should be H plus. It's the negative log base 10 of the concentration of H plus, but we know there is no H plus, it's really H3O plus. So pH is the negative log base 10 of the hydronium ion concentration. Okay? That's what it stands for. You can have P of a lot of things. We can have POH. That's going to be the negative log of the hydroxide ion concentration. So P in front of something like that just means negative log base 10 of whatever it is. Okay? You know a few things about pH, and one of the things you know is that if you have a pH of 7, it's neutral. Well, what does neutral mean? Why is it neutral? I mean, does that mean it just doesn't take a side? It's just like, oh, I don't want to take a side. No, what does neutral mean? Well, neutral means that the concentration of hydroniums is equal to the concentration of hydroxides. When does that happen? Well, we'll get into that in just a second. So if neutral is when hydroniums and hydroxides are equal, then what is it when hydroniums are greater than hydroxides? Well, we say that's acidic. Acid, when there's more hydroniums than hydroxides, it's acidic. When there's more hydroxides than hydroniums, we say it is basic. More base than acid, therefore it's a basic solution. Acidic when there's more acid, basic when there's more base inside there. And then when it's exactly at 7, it's neutral. But what does that neutrality mean? Well, we got to go into water. And water is very, very special in so many different ways. But in this way, it's very special. Water is what we call amphoteric. What does that mean? Water is both an acid and a base, depending upon the situation. If you took a bowl of water, just set it down on the counter, and it was pure water, and certain temperatures, whatever it is, the water is going to self-ionize, and it's going to form hydroniums. That is, one of the waters will donate a proton to the other water molecule and form a hydronium. And then the one that donated, it's going to have lost a proton, and therefore it's going to be negative. And this is where the Bronsted-Lowry definition really becomes valuable. So something which donates a proton can then accept a proton, right? I mean, if it had a proton and it donated it, clearly it can have a proton again because it had one and donated it. So the Bronsted-Lowry definition of an acid, it donates a proton, but now it can accept a proton. Bronsted-Lowry definition of a base. That's what we call a conjugate base, co-joined base. An acid which donates a proton can now accept a proton. Therefore, when an acid donates a proton, it becomes the conjugate base. Well, this is the water molecule that donated a proton to the other water molecule, and it is now a base. This one accepted a proton from the other one, and now it can donate a proton because now it's the conjugate acid of a base. So anytime we have an acid and it donates a proton, it becomes its conjugate base, co-joined base. Anytime you have a base which accepts a proton, it then becomes its conjugate acid, co-joined acid, because if it accepts a proton, it's a base. Now it could donate a proton and become an acid, so it becomes an acid. Water is both. It can donate a proton or it can accept a proton. And in fact, it self-ionizes. We have an equilibrium here. If we have an equilibrium, we have a mass action equation. Kw, W for water, is going to be equal to what? Products over reactants raised to the coefficients from the balanced chemical equation. We did that before when we're talking about coefficients. So what is that? Well, that's going to be H3O plus times OH minus. We don't include the water. We don't include the water because this is an aqueous solution. Aqueous means in water. And the molarity of water doesn't change for the small amount of hydroniums and hydroxides are being produced. The molarity of water? What does that mean? Well, sure, water has a molarity. What's molarity? Molarity is moles per liter. If I have a liter of water, it has so many moles of water in it. How many? Well, if it's 4 degrees and all this other technical stuff, a liter of water is about 1,000 grams, right? Because the density of water is about 1 gram per milliliter. So if a liter is 1,000 grams, and each mole of water is 18.01 grams, we can figure out how many moles of water there are in a liter of water. And that's the molarity of water, moles per liter. Turns out it's about 55.6 molar. And that doesn't change when we have a tiny bit of the hydroniums and hydroxides that show up. So this is a constant. Clearly, then it has a value to it, and the value is 1.00 times 10 to the negative 14. And this is a constant. That tells us that the concentration of hydroniums times the concentration of hydroxides always equals 1 times 10 to the minus 14. Wow, that's interesting. So what that means is that if the hydronium ion concentration goes up, the hydroxide ion concentration must go down to maintain this 1 times 10 to the minus 14. It also tells me that if I know my hydronium ion concentration, I can calculate the hydroxide ion concentration. If I know the hydroxide ion concentration, I can calculate the hydronium ion concentration because they're equal to a constant over there. Let's do an example of that because that's valuable to know and use. Let's say I have a solution which has a pH of 8.0. Okay? So what is my hydronium ion concentration? Well, there must be some relationship since pH is the negative log of the hydronium ion concentration, so there must be an easy way to calculate the hydronium ion concentration from the pH. Sure, if it's the negative log of it, then I take the anti-log of the negative of it, and that'll give me back what it was. Anti-log is 10 to the negative pH, which is 8.00, and you don't need a calculator. This, you can clearly see, is going to be 1.00 times 10 to the negative 8 molar. That's going to be my hydronium ion concentration based on a pH of 8. Perfect. That's beautiful. What's my hydroxide ion concentration? Well, I know that my hydroxide ion concentration times my hydronium ion concentration, 1.00 times 10 to the negative 8, has to equal 1.00 times 10 to the negative 14. Okay, then I just solve for hydroxide. My hydroxide ion concentration then is clearly 1.00 times 10 to the negative 14 divided by 1.00 times 10 to the negative 8. You don't need a calculator for this. You know you're dividing by the negative of it. That means you add the positive to up here, and we get 1.00 times 10 to the negative 6 molar. We had a solution pH of 8. pH of 8, is that basic or acidic? It's greater than 7, so it's basic. Basic means that there's more hydroxides than there are hydroniums. Did we end up with more hydroxides than we did hydroniums? Oh yeah. 10 to the minus 6 is much, much greater than 10 to the minus 8. Okay, 10 to the minus 8 is much smaller. So that's kind of things you always want to come up with ideas that you can use on an exam to make sure that you did the math correctly. So if we have something and we have a pH that's greater than 7, then we would expect that the hydronium ion concentration is going to be smaller than the hydroxide ion concentration. So why is pH 7 neutral? Because the only way we get a pH of 7, which means the hydronium ion concentration is 1 times 10 to the negative 7, has to be if the hydroxide ion concentration is the same, right? Because 1 times 10 to the minus 7 times 1 times 10 to the minus 7 gives me 1 times 10 to the minus 14. So it's neutral because the hydronium ion concentration and the hydroxide ion concentration are equal. But with this constant, anytime the hydronium ion concentration increases, the hydroxide ion concentration decreases, and vice versa. Okay, that's really pretty much all you need to know to be able to do this lab. But let's go through weak acids and bases because that's going to be really valuable for buffers, like I said, and it's interesting. Strong acids and bases, they're not so interesting. I mean, for a strong acid, we know strong acid means what? 100% dissociates. Therefore, if I have a strong acid like HCl, HCl plus H2O is going to go to give me H3O plus Cl minus. For every mole of HCl that goes into solution, I get a mole of hydroniums. Therefore, if I have a solution that's 0.0100 molar in HCl, it's going to be 0.0100 molar in hydroniums. Okay? There's nothing, that's nothing interesting about that. That's not very interesting. Weak acids and bases, they're interesting. And they're interesting because, well, they're weak acids and bases. They don't fully dissociate. In fact, a lot of weak acids and bases only dissociate about 2 to 3%. Very, very small fraction of that. So that makes for some more interesting chemistry and stuff. So let's go through an example of that and make sure we can understand what's going on. So we'll do the example that's in the handout. And that is we want to find the pH of a solution that's 0.152 molar in thiophenol. And they give us the C6H5SH acidic solution. Wow. Don't worry about the structure of the acid. Structures of acids are important in situations, but not in the situation where we want pH. If we want pH, we got to get hydronium ion concentration. That's our focus. We don't care about the structure of the acid. All we need to know is that it's a monoprotic acid, and then they tell us the pKa, and we do need that. Whatever the heck pKa is, 6.520. So we can do that. That's all we need to know. We don't even, you can just say generic acid. Doesn't matter. Got a pKa, got a pH, got a molarity. We can calculate out the pH. How? What do? We start where we always start, the balanced chemical equation. But you say, but you told me I don't care about the chemical structure. You don't. All you need is the generic acid equation, and that is HA, that's my acid, plus H2O, water, goes to give me H3O plus A minus. A minus is the conjugate base of the weak acid. Here's my weak acid, there's my conjugate base, there's my base, there's my conjugate acid. Remember, acid-base pairs, they always go together. Conjugate base, conjugate acid. So this is acid, this is conjugate base, this is base, this is conjugate acid of that base. Okay? So if this is an equilibrium, that means there's a mass action equation. Ka equals products over reactants raised to the coefficient from the balanced chemical equation. That is H3O plus times A minus all over top of HA. Again, water's not included because its molarity does not change. All right, so let's fill out our Ka in here. Well, what do we got? pKa. What's P? P means negative log base 10 of it. So to get the Ka, then is equal to 10 raised to the negative pKa, negative 6.520. And that gives us a value of what? 3.020 times 10 to the negative 7. Okay, so let's fill that in. 3.020 times 10 to the negative 7 is now equal to my hydronium ion concentration times my A minus all over top of HA. Okay. I've got three unknowns. I don't know what the hydronium ion concentration is. That's what I'm looking for, pH. I don't know what the A minus concentration is, and I don't know what the HA concentration is. I know the molarity of the acid as it went into solution, this value here, which we call the analytical concentration, that usually given as CHA, 0.152 molar. That tells me how many moles of acid did I put into a liter of water to make my acidic solution. That I've been given. But once it's in there, some of it forms A minus, some of it forms HA. I don't know how much is this form. I don't know how much is that form, so I don't know what the concentration is. I got three unknowns. I can't solve it. So I've got to do something to simplify. I've got to get rid of some of the unknowns. So the first thing to get rid of the unknowns is I use the analytical concentration, and I use Lavoisier's conservation of matter. Lavoisier was a fantastic scientist. Came up with a big scientific breakthrough when he found out that matter is conserved in a chemical reaction. I know you say, gosh, how hard could that have been to figure out? Well, a lot of things aren't conserved. Color's not conserved, volume's not conserved. There's a lot of things that aren't conserved. So it was very interesting. It was very difficult, and it was a big step forward in science when Lavoisier found out that matter was conserved. It led to everything else. So Lavoisier's conservation of matter says that if I have a molarity of my acid as 0.152 molar, and it can either take this form or that form, the sum of these two forms must equal the molarity of the acid that I put in solution. Therefore, Lavoisier's conservation generically is CHA must equal HA plus A minus. For our purposes, that means 0.152 must equal to HA plus A minus. Make sure you understand that. It can take on two forms. Some of the HA can ionize to form A minus. For every A minus, there's an HA loss. Therefore, the sum of these must equal what the molarity was originally. Well, what I can do with that is I can then rearrange that, and I can say, okay, then HA is equal to my CHA minus A minus. And I know what CHA is. So if I take this definition and plug it in here, my equation becomes 3.020 times 10 to the negative 7 is now equal to H3O plus times A minus, all over top of 0.152 minus A minus. I got rid of one of the unknowns. The HA is gone. I now have just A minus and hydroniums that I don't know what it is. Still, two unknowns, can't solve that. So I need to make at least one more simplification in there. First one was Lavoisier's conservation of matter. That was not an assumption. It was just a known. It was it's what it is. Now I need to make an assumption. What can my assumption be? Well, let's look at things. I notice up here that for every A- form, there is a hydronium form from my acid. But if that was the only source of hydroniums, if the only source of hydroniums came from the HA, then I could easily, you can see where I could say that my hydronium ion concentration was equal to my A- concentration. And if I plug that in down here, then I would end up with 0.020 times 10 to the minus 7. A- becomes hydronium, so that's hydronium squared. All over top is 0.152 minus, substituting in hydroniums down here. Well, that only has one unknown. That would be great. I could solve that. It's actually a quadratic equation, but I can solve those. So why can't I say this? Well, there's two sources of hydroniums. There's the hydroniums that come from the water, from the acid protonating the water. And there's the hydroniums that come from the self-ionization of water, right? Water is going to form hydroniums plus hydroxides. But if we think about it, because this is equal to 1 times, because the concentration of hydroniums times the hydroxides equals 1.00 times 10 to the minus 14. As the hydronium concentration goes up, the hydroxide ion concentration goes down. You know that. And it starts off pretty small to begin with, right? There's 1 times 10 to the minus 7. This is 1 times 10 to the minus 7. As I crank up more hydroniums due to my weak acid, this goes up, that has to go down. Well, look at the water. For every hydroxide formed, there's a hydronium formed. So if the hydroxides go down, the hydroniums that come from the self-ionization of water also go down because it's 1-to-1. 2 waters form a hydronium and a hydroxide. If the hydroxide concentration gets pushed way down, then the concentration of hydroniums from the self-ionization of water gets pushed way down, and it wasn't very big to begin with. Therefore, I can say the hydroniums that come from the acid are much, much, much greater than the hydroniums from the self-ionization of water, especially because this is an acid suppressing this. Then I can say hydroniums equal A-, and I can end up with my quadratic equation. So that ought to work. I mean, that's a good simplification, and it's very, very strong simplification. So with that, I've got a quadratic, and generically the quadratic is always H3O plus squared plus Ka times H3O plus minus Ka times CHA equals 0. And you know how to solve a quadratic. For ours, this specific case, it's H3O plus squared plus 3.020 times 10 to the negative 7 times H3O plus minus 3.020 times 10 to the negative 7 times 0.152 equals 0. And if you solve that, and I suggest you do, I mean, it's pretty easy to solve quadratics, so you should be able to do that. You should get 2.141. Of course, you got to throw out the extraneous root. Remember, when you do a quadratic, you always get the b, the minus b and the plus b, so you get an extraneous root that you have to throw out. 2.141 times 10 to the negative 4 molar, which means that my pH, which is the negative log base 10 of my 2.141 times 10 to the negative 4, is going to be 3.669. And that is the right number. Sig figs there. The log sig figs are a little bit weird. I'm not going to get into that, and I'm not going to hold you responsible for it, okay? Now, I could go on, and I could make another simplification, which makes this even easier, but that's a different kind of assumption, and you have to verify it and everything else. If you're a chemistry major and take analytical chemistry and have me, I'll explain all that to you and tell you how to do that. Otherwise, you've got everything you need to be able to do this lab. Like I said, this lab is pretty simple. You're going to have to calculate out the hydroniums based on the pH and calculate out the hydroxides based on the hydroniums, but we did that already, so you should have no problem doing that. Basically, you just measure the pH of a solution that is concentrated, then you dilute it, measure the pH of the dilute solution, see how it changes. Why would the pH change on dilution? Look at the definition of and then calculate out the hydroxides for both of those. So it's a lot of the same calculations over and over again, not too many. It won't take you very long to do it. But you should be able to do those calculations, get familiar with them because they are important. And then understand this, because next week we're going to do buffers, and buffers takes from here and goes in a different kind of direction. Okay? So hope you can stay safe. Hope you have fun. And I'll see you next week.